Okay, so I think we're going to get started. My name's Nick Sullivan, and this is a little bit about me before we start. So I do sort of cryptographic engineering as well as security research, programming, computer programming, stuff like that. I work at a company called Cloudflare. It's a sort of cloud security, website security, DDoS protection, encryption kind of company in San Francisco. I work at cryptography at scale, and I do a little bit of building, a little bit of breaking, a bit of both. So what I'm going to talk today about is randomness, right? So what is randomness? Why is this important? Why is this something that we should talk about at a hacking conference? So this is what I'm going to talk about through this presentation. So yeah, what is this word, randomness? I mean, everyone sort of intuitively knows that random numbers are something that you can't predict, but how do they tie into security systems, and how if you have randomness that's not really random, how can that cause your security systems to be completely broken? So in this talk, I'm going to do two kind of short demos of what happens if your random number generator is bad. One is Bitcoin and one is TLS SSL. I'll get to that but essentially I'm going to be demonstrating Bitcoins that I stole from somebody yesterday, and a site that I set up that anybody listening over the wire can decrypt the TLS SSL session, even though it's fully encrypted. All right, so random number generators can be compromised in a number of different ways, and I'm going to, I guess, talk about both of them here. One is explicit subversion, so if you intentionally design a random number generator to be not so random. And another way is if the algorithm itself was designed with a weakness or an implementation flaw, and random number generators have to be seeded. They have to start with a seed, and if your seed is the same, your numbers are going to be the same. So all three of these situations are exploitable. So let's just step back a bit and just talk about the internet and how it's broken. And well, a lot of people have kind of wisened up to this outside of this community over the last year or so. There's been slow adoption of a number of different things that people are trying to do to improve security, DNSSEC, perfect port secrecy. It's coming along, but a lot of websites still don't use this kind of stuff. And fundamental parts of trust on the internet are broken, such as revocation. We found this out, well, everyone who has been working with it closely has known for a while, but with Heartbleed and all the different certificates that have been revoked, it's been pretty much shown that on the web, revocation is completely broken. So it's been kind of a trying year, an interesting year for people who haven't been, I guess, in the know for a long time. And a lot of the threats to the internet and to security and to secure communication have moved from theoretical to concrete. And a lot of bugs that may have been known by some people over a long time are now kind of known to everybody. And the opinions of this quote-unquote paranoid, which would include a lot of these people in this room, have now kind of moved to more mainstream opinions. And these leaked documents, I can talk about it because I've never actually worked at the NSA, but there's sort of been purported attempts to subvert public standards and open source projects. One of them is subversion of random number generation. So random numbers, what can you actually do if you subvert the source of random numbers? This is an icon you might have seen. But dual ECDRBG, I mean, Dickie talked about this earlier, and it's an algorithm, and RSA apparently took 10 million to make this the default in BSafe, and that's their cryptographic algorithm, and they turned that off 9 years later in 2013. But so what it is kind of this chunky, slow, random number generator based on elliptic curves. So you start with a seed, and it gives you, a sequence of random numbers. And at least in the NIST standard, it came with 2 starting points. that are elliptic curve points. And as Van Stone and Brown patented in 2005, if you know the relationship or you choose the relationship between these two starting points correctly, you can actually predict the rest of the random stream. And if the two starting points in the NIST standard were actually chosen completely at random, then that might have been a missed opportunity. But in any case, that's what proves that this sort of random number generator, if they're chosen at random, then it should be safe. But if they're chosen kind of maliciously or intentionally, then if you read 32 consecutive bytes, you can typically decrypt the rest of, or figure out the rest of the entire stream. And the reason for that is it has this feedback loop construction. So every time that it spits out data, it comes right from the initial state. Nothing additional gets added in. So you have G and F, which are elliptic curve operations, and they kind of feed back in to the state, and it outputs data. Now, dual EC, DRBG, and BSafe was the random number generator for SSL, for TLS. And as I said before, if you have 32 bytes, you should be able to figure out the rest of the random stream, but the client hello, which is where the client actually spits out some random numbers to the server to help establish stuff, is it only uses 28. The last 4 bytes are a timestamp, or at least that's what the standards say that they should be. So I'm not going to read too much more into this, but RSA implemented something called the extended random TLS extension, where in the handshake they gave a bunch of extra random. So that was the reasons for that are not super clear to me, but in any case, if you implement extended random, then you get the full 32, and if you know the points ahead of time, if you're the person who built them, then you can get the rest of the random stream. So this year there was a paper that came out on the exploitability of dual EC, and they looked into different implementations of SSL, TLS, such as OpenSSL, S-Channel from Microsoft, BSafe, and they built their own Trojan points, I guess, and they found that each of these different SSL implementations are fingerprintable, and you can actually figure out the session key in seconds for some of these. And this doesn't require any active interception. It just requires you to, or it doesn't require any active injection, but you can just sort of passively listen to the handshake and figure out the entire session key in seconds, or up to hours in the OpenSSL case, because they do a little bit of wacky stuff. But so the takeaway from this algorithm and just the discussion about this is that many protocols actually include random values in just throwing it into the protocol. So these are typically stuff like IVs for like chaining mode cryptography, session IDs, nonces. These are random values, and if these come directly from the random number generator and you know something about the random number generator, these can give you some kind of clues. And so for the case of the Trojan points for dual EC, you can recover the internal state of the random number generator with this data. And all future random can come from the internal state. So that's one thing that's been in the news about random number generators lately. Another one is Intel's read-rand instruction. This is something that was introduced in their Ivy Bridge processors, and later in Ivy Bridge and later, so Haswell, Broadwell, everything further. But it's a random number generator that's built into the CPU, basically. And it's designed to be fast and convolutes a bunch of stuff. And then there's an AES encryption step at the end. So this whitening step kind of makes sure that it's statistically random and unpredictable. And there's sort of been guesses, it's hard to tell, but people have been talking about maybe right there in this little point right here, which is where the AES key is, there's a potential for a backdoor in that part of this implementation. So this is a hardware instruction. If you want to get this random data, you just call this CPU instruction. So if you're in a kind of virtualized environment, this CPU instruction can be controlled by the hypervisor and overridden. And as well, if you have microcode updates for your CPU, that's where you can kind of switch around what the output of this thing is. And so the designers apparently haven't, they used their electron microscopes and looked at the original Ivy Bridge ones, but they haven't necessarily looked at the chips in Haswell. And is there a backdoor in the silicon? It's actually really hard to tell in this case. But theories are yes or no, but most likely no. So why does this matter? Or how does this come into the way that randomness is used for the internet or for anything else? Well, Linux and FreeBSD had some kind of mysterious patches that were submitted that tried to make RDRAND the only source of entropy for dev random on the system. And eventually these were reverted, and they decided to go with the standard technique, which is to use the algorithm, the dev random pool that's in the kernel itself, and just mix the read random extra data in, and they consider that to be okay. So randomness can come from hardware. This is pretty interesting on commercial hardware now, I guess. Like on regular CPUs, you can get really fast randomness from hardware, but do you trust it? You should probably mix it with other sources, and looking at the random values itself doesn't reveal backdoors. And this last point, I haven't explained why that is. So let's take a step back and talk about entropy for a bit. So what is entropy? This is kind of a amorphous sounding term, but yeah, this explains why read random might be dangerous on its own, but it's totally fine to mix in with other sources. And the reason for this is, for cryptographic needs, statistical randomness doesn't tell you anything. So if you have a stream of data and ones and zeros occur as frequently statistically through the entire stream, that doesn't tell you one thing or another about whether or not this stream can be used in cryptographic applications. So what you need for cryptography is for the random stream that you're using to be unpredictable and to have high entropy. Now let's go back to this entropy idea. What does it mean to have high entropy? Or what is entropy? And just in kind of layman's broad terms, it's how much information is in data. How much really new things are you revealing when you read a piece of data? So an example I like to use is the digits of pi. They're very, very statistically random, but they're completely predictable. So if you know that you're looking at the digits of pi, and you have 5 in a row, and you know where that is in the sequence, you can figure out what the rest of them are. They're really not random. They have no entropy. And entropy is how much information. So if you have a stream of digits that are just the digits of pi, how much information is in there? Well, it's just as much as the sentence, the ratio of circumference to diameter of a circle. Right? So that doesn't take very many bytes. There's not a lot of entropy in the sequence of digits of pi. And this kind of points out that entropy is really, it's in the eyes of the beholder. It's not a universal quantity. It depends on what you know in advance. So if you didn't know anything about math, the digits of pi could have a lot of entropy to you. There's no way for you to predict them. And one sort of example that illustrates this, people talk a lot about the NIST random number beacon, right? This is a project where they advertise a new block of signed random data at frequent intervals, and they're kind of chained together in this hash chain, and it's like provably, comes from like quantum information or sort of quantum interactions, and it's kind of like, quantum theoretically random, but they're publishing it. So it's not, everyone has all the information about a piece of NIST random data. So it doesn't really have any entropy because everyone in the world has access to it. So it's really about the difference between the knowledge you have and the knowledge to predict the next sort of stuff. So even if you can generate it with a high entropy source, if you tell everyone about it, it's no longer secret. And this is kind of the idea with keys in cryptography. If you publish your key to everyone, then there's no entropy. There's no information that someone can learn by learning your private key. So let's step this back a little bit and talk about how this entropy ties into random number generators. This is getting a little crypto-y, but I'm sure you guys can handle it. If you encrypt the digits of pi with a private key, or like a 128-bit AES key, and then you tell the world this stream, you give the entire stream, then to you the entropy is nothing, right? Because you have the key and you can compute any piece of the entire sequence. But to the world, they have to either crack AES or know that private key. So it's 128 bits of entropy to the rest of the world and none to you. And this like gap of knowledge is what you need for random number generators. So this 128 bits of randomness, this is also the same entropy that you get from a stream of dual EC DRBG, right? So if you have, it's derived from, as I mentioned earlier, 2 points P and Q. And if you know the points ahead of time and their relationship, then you can figure out the rest of the stream. So to you, the stream has no entropy, but to someone else, they have to solve the elliptic curve discrete logarithm problem. If they can find this n, this relationship with P and Q, which exists for any 2 points, then they all have as much information as you. But just like cracking that AES key for the digits of pi, cracking this relationship, it takes approximately 128 bits to do, because the elliptic curve discrete logarithm problem is known to be hard, and it's known to be a square root of the size of the field that you're working in. And the size of the field that's for dual EC is 256 bits. So one stream of dual EC, 128 bits. If you don't know the secret, none if you do. So independent entropy is kind of additive. So if you have 2 dual EC streams and you XOR them together or add them together, you're going to basically double the entropy unless they're related in some way. So any independent sources of randomness can be added together, and you'll get more randomness. So that's why it's OK to take read rand, even if there is a backdoor, and tie it into whatever your source of randomness is. Because if you mix stuff in, it's always going to increase. It's never going to decrease. So that's kind of covers the background of entropy and randomness and what all this sort of means. Well, how do we apply this? Well, let's talk about the digital signature algorithm. This is a pretty old cryptographic primitive, and it was, I guess, proposed in 1991. It might have been known ahead of that, but this is when it was publicly proposed. And it allows you to do a digital signature. If you have a private key, you can sign a hash of a message and prove that you authorize it, or you authenticate it, or whatever. And there's a corresponding public key, and anyone in the world can verify. So only you can sign, and anybody else can verify. And where's DSI used? Well, everywhere. It's used almost everywhere. Like, what kind of key is your SSH key right now? Like, raise your hand if you have exclusively RSA-based SSH keys. Right, it's nobody. So everybody uses DSA, and elliptic curve DSA is it's a variant. It's basically the same algorithm, but instead of over prime fields, it's over elliptic curves. It's basically the same sort of thing, and it's used in TLS and in Bitcoin. So this is going to come up later as I show how to exploit this situation. So the core complaint, or the main kind of downside to DSA and ECDSA, is that you really need pure random, like cryptographic random numbers or unpredictable numbers to use it safely. Every signature that you make takes some random values, and if you use the same random values twice, your private key can be mathematically computed by anyone who sees those 2 signatures. So at kind of like a high level, you pick a random value k. If you're going to create a signature, and you convolute this k with your private key and the hash of the message, and you publish these two values r and s. R is based on the random value k, and s is the convolution. And if you can solve the discrete logarithm on r, you get k. So this is where your knowledge gap is. So this random k is like an exponentiation. So you have to do a discrete logarithm to get back to k. And if you have a known k on any signature, you can extract the private key. And if you repeat the same k on any two signatures with the private key, you can extract k, and then you can get the private key. So it's really dangerous to use DSA with non-random random. So here's the math. You can kind of, this is like the algorithm taken from Wikipedia, but there's a couple steps. You take a hash, you take some exponentiations, and you can verify it this way. And then to break it, you can just take the two equations, subtract them together, do a little bit of algebra, and voila, you have your k, and then do a little bit more algebra, and you get from the k back to the private key, and you're done, and your key is gone. So Bitcoin is, as everybody here knows, Bitcoin is this digital cryptocurrency that's gained a lot of steam and actually has a lot of value in the world right now. And the fundamental security, the reason that Bitcoin is what it is it's based on ECDSA. So if you want to spend a Bitcoin or a fraction of a Bitcoin, you basically have to use ECDSA. That's how identity works in Bitcoin. Your public key in your ECDSA key pair, that's your Bitcoin address. And your private key is what allows you to spend the Bitcoins you have. And if you create a transaction in Bitcoin, the way it works is you have your address and somebody else's address, and you say, I want to pay X number of Bitcoin from my address to this person's address. You sign it with an ECDSA signature and send it out to the world, I guess. And then everybody else in the network sort of verifies the signature, and it gets added to the public ledger. And that's how Bitcoin works. It's just a sequence of transactions, A to B, with X amount of, how much you transfer each time. So it's really a fully deterministic public list of every transaction that's ever been done, which is kind of goes against some people's idea that Bitcoin is an anonymous currency. It's absolutely not an anonymous currency. It's a fully public ledger of every transaction that's ever been done. But there's this operation. So Bitcoin has its own kind of language based on, it's kind of like Forth, where you can verify that a signature is made from a transaction. And two transactions by the same Bitcoin address, as I said earlier, if you use the same random value k, then you're going to get back to what the private key is. And in Bitcoin, that's really bad, because then you can just spend everything else that's in that account. And these S and R values are the same S and R values I was talking about before, and they're public on the public ledger. So every transaction that's ever been done with Bitcoin has this R and this S. And if you go through the list and find something where R1 is equal to R2, that's a typo there, then most likely they use the same random K. So that wallet is compromised. So I'm going to do a little demo here. Let's see. So yesterday I worked with some reporters from CNN just to demonstrate this. So this is the address. I can't really see very well, but this is one of the addresses of this wallet that we wanted to compromise. And so this is one transaction, and this is another transaction where we're paying out of this wallet. And if you go here, you can see this is what the transaction looks like on blockchain, and this is what the second one looks like. And these input scripts right here, this is the public key of the person who spent the Bitcoin, and then this is the R and the S. This is the digital signature algorithm. It's actually pretty hard to see here, but if you, let's see, if you look right here, this is the R, and for this one, this is the R. It's the same value. So you have the 09AC222. So the way that this worked is I basically recompiled the Bitcoin tool, basically the Bitcoin official, which uses OpenSSL for its random number generator. And OpenSSL has a really nice thing where you can just hook the random number generator. So if anyone out there is using Bitcoin that has a random number generator that's hooked, you can do this sort of thing. And without knowing it, all of these two signatures will be the same. So what can you do with that? Well, if you can, so I basically put together a little script that does the mathematics of reversing this Bitcoin. So if you can see right here, you enter in the hash values and of the message that's being signed, and then the signatures itself, and it computes. You see here, R1 and R2 are the same for the two signatures that we did, and it outputs this key. So in practical terms, what does that mean? Well, let's just create a free wallet on blockchain, and now I can't really see this very well, but I think it says YPFYE. Okay, whatever. This is our wallet right here. Welcome back, and then we have to log in again. This is a very aggressive security policy on the site, as it should be. Okay. All right. So what we can do right here is this says advanced warning, but if you have the private key of someone, you can just go to any public blockchain site or even on your Bitcoin client on your device, and if you have the private key, you can just go add private key. Voila. This is Erica's address. This is the address that we hacked, and input directly, and there you go. We now have in the wallet, well, there's nothing left in this because obviously anybody in the world could do this. But so we didn't leave any money in there. But yeah, so now we have total control of this address. So if this address is like a donation address, or if it's something that anyone else has been using, then it's compromised. And you can search through the blockchain. There are a number of these accounts that have been compromised in such a way. So it's actually not that difficult. So that's one way that DSA can be used to compromise something that's actually of a lot of value in terms of Bitcoins. And what other places can you compromise stuff? Well, VPN signatures. IPsec uses DSA, EC, and DSA sometimes. OpenVPN does too. As I mentioned earlier, everybody's SSH keys, they're DSA. If your random number generator spits out the same number, someone could maybe steal your SSH private key. Secure boot chain, same sort of thing. Code signing, this is all sort of like client related. Either if there's a bug or a subversion in your random number generator, you can lose a lot of stuff. So what are the symptoms that you've been breached by this? Well, in terms of if you have signed the same thing twice, you can look at the R value and see that you signed the same thing twice and then just give up on that key. But if someone managed to predict what the K is going to be, there's no evidence that anything's compromised. Well, okay, so that's DSA. This is I'm going to go through the gamut of the standard cryptography sort of functions that we've used forever, these algorithms, and RSA is probably one of the oldest, right? So it's a public key crypto system, and the PKI on the internet is still almost entirely based on RSA. So trust on the internet, this is what it's based on. And as everybody probably knows here, it's based on factoring. So when you create a new RSA key, you generate two kind of random looking numbers. And if they're prime, you can multiply them together, and you can use it to create a RSA key pair. So this is what the Taiwanese government did. They had in their smart cards with IDs, and they generated a unique RSA key on each of these smart cards. And so factoring's hard. That's how you solve RSA. You factor P and Q. But if somehow someone created P times Q and then the same P again in a different RSA public key, then it's actually easy to factor, because there's something called the Chinese remainder theorem. You can just look for common factors between the two, and it's incredibly easy and fast to factor these quote-unquote secure RSA keys, because they have a cofactor. So you can do this efficiently too for if you have a large numbers of these RSA public keys, these P times Qs. And this is a talk that came out last year. Was Henninger, Longa, and Bernstein did this for the Taiwanese government. They took a look at all the public keys for each one of these identifiers for these individuals, and well, they found that some of they mutually factored quite a few of them, like dozens and dozens. And then the ones that they did find, they took a look at what the primes look like, and some of them look like this, with a lot of zeros in the middle. That does not look like a random prime number to me. And look at the second one. It has all these kind of repeated patterns, and apparently it was they didn't use a secure random number generator to generate these primes. They just used some kind of bit swapping non-cryptographic number generator. So as a result of bad entropy, so they actually extrapolated from the ones that they did find to find a whole slew of other kind of primes that are formatted in the same kind of way, ones that you would have gotten from this kind of crappy random number generator. And they factored tons and tons and tons, I think over 100 of these identities for Taiwan. And so there's no demo here. Factorable.net is where all their research is from this. But this is the result of bad initialization and using a bad random number generator. It's hard on smart cards and low-power devices to actually get seeds that are really random, that if you don't have something in hardware that's using physical properties to generate random numbers. And this is sort of what happened here. So if you're going to attack something like this, you need to attack before the keys are created, or you have to know how the system looks before the keys are created. And RSA keys are generated in a lot of different places, as you might know. PGP is a great example. You generate an RSA key if you're generating a new identity. So you have to do this pretty securely if you want to trust this PGP identity. This is something that is difficult to do. A lot of times people just pipe the data from dev-random or dev-urandom and just trust whatever the system gives them. And if the system has a flaw in it, or whether intentional or not, then after the fact you can go back and figure out people's keys. So this is also routers and embedded devices. It's even harder because there's no hardware source of random number generators on these sort of things. So it's definitely ways to look for compromise. And well, what are the symptoms that you've been compromised in this case? There's none really. I mean, there's no way to know. There's nothing active. This is just passive. You read your primes and you factor it. And if anybody's looking for places to actually implement this attack, you can just scan the internet. Just ask any IP address, and they'll spit back the public certificate, and that'll have an RSA key. And who knows? It could have a common factor with something else. Same thing with the PGP lists of public keys. Keybase.io is this new thing that people are talking about, collecting public keys. It could be a good way to take a look at what the public keys for everybody is out there and which ones might have a common cofactor. Now those were two kind of esoteric examples. Let's talk about TLS, or this used to be called SSL, but it's the encryption layer for everything on the internet and usually between endpoints, and it's very commonly used. Anything HTTPS uses TLS, and if you break this, then you lose privacy on the internet. And this is a really good target for if you are, some kind of nation state or something like that. If you want to actually be able to read the information that is exchanged by people in your country or people in other countries, this is the way to go, because people assume that this is secure if there's a little lock icon. And yeah, so in a little bit I'll have a demo. I built a little site that has a bad random number generator, and we're going to steal some passwords. But so there are two ways of establishing. So just to go back, TLS is there's two components to it. There's encryption and authentication. Typically on the web, authentication is how the server proves that it is who it is, and this involves a public key inside a certificate that is signed by a certificate chain that goes to a root authority. And every time that you connect with one of these servers, you establish a session key, and all the communication is encrypted with this session key back and forth. And it has to actually establish the session key, you have a handshake, and this is how TLS starts. And RSA was the original way that SSL was created. And to get to the session key, essentially what you do is on the client, they create, through random number generation, the session key, and then they encrypt it with the server's public key, send it to the server, they decrypt it. So it's really the client that picks the session key in this case. And lately, people have been moving to Diffie-Hellman-based TLS. So this is where the handshake is separate from the public key. So the public key only proves, the public certificate key only provides authentication. And so if any time in the future you go back and you have stolen the private key, you can't go back and extract the session key from this communication. The key only provides authentication. And the way this happens is through our classic key exchange algorithm, Diffie-Hellman. And this also didn't take up full adoption until people started using elliptic curve Diffie-Hellman, which is just a lot faster and scalable for the internet. But the interesting point here is that it's not just the client that generates the random value for the session key. It's not the client that provides the seed from it. It's a combination. There's a random from the client and a random from the server, and they get combined with Diffie-Hellman. So for example, this is kind of like what it looks like on the wire in the middle of a handshake, but the client sends A times G, where A is their ephemeral private key, and the server sends B times G, which is their ephemeral private key, and this is all in yellow in the middle. And the pre-master secret, this is what is used to derive the session key, is AB times G in elliptic curves. So if you know A or if you know B, then you know the session key. And that's the crucial part here about this demo is, well, there's three different things you can do. So for RSA, if you have a compromise on the client, you can create the session key and steal it from there. This is if you have a dual EC implementation with the points of your choosing, this is something that you could potentially do. ECDSA, which is this should be ECDHE. Okay, no, there is ECDSA, which is if you have this is not really popular yet, but your client certificate can be on the server, it can be a RSA key or an ECDSA key. 99.999% are RSA right now. But Gmail has moved to ECDSA, and some of the rest of the internet is coming along that direction. But yeah, if the server has a randomness bug or randomness predictability problem, then you can potentially lose control of the way to authenticate the server. And the Diffie-Hellman version is vulnerable to both client and server. So if you have a bad randomness on the client or bad randomness on the server, the session key is yours. So here's a little demo. So I set up a Node.js server with a slightly modified OpenSSL implementation. And let's take a look at this. Yeah, so this is a regular internet site, and it's fully secured. Here's HTTPS, and here's a little lock that says, you know, this is an authentic site. This is signed. So everything that you send over here should be. I'll just put one of my friends' logins here, and right. So then you can kind of log in, and let's see. I'm just here sniffing over the wire. This is something that if this was over a unencrypted Wi-Fi, then anyone else here could do the same sort of thing. You just sniff the handshake, take the two parts of the Diffie-Hellman key exchange, and if you know either on the server side in this case that what the randomness is, you can construct the session key and you can do the decryption. So as you can see right here, it just spits out everything that was over TLS. This is the body of the data. So this is totally transparent to anyone using any of these websites. So if you have a site out there that has a random number generator that's been compromised and you can't predict, you can't see there's no evidence to you that anything's been compromised. There's no exfiltration. There's no outbound packets. All there is standard looking traffic with random data that looks random. And anyone, if they're able to kind of sniff this over the wire or at the ISP or the internet exchange, anything like that, can go through and decrypt the entire session. So that's also pretty easy to do. Let's see. Where is my mouse? Okay, so these were the kind of demo proof of concepts, and I'm going to try to inspire you guys to find your own ways to exploit random numbers. And there are different layers of the software stack that you can use to attack this. So in the application layer, I used a Node.js server, and I just actually made modifications in Node. If whatever your tool chain is compromised, or potentially like you get an update to your tool chain, and someone puts a hook in there, everything will look normal, but your random numbers will be compromised, and your whole security will be compromised. You can rely on shared things in user land. In the kernel, dev random, you can have it point to something else. Or modify the timing. More interesting is like virtualization. If your software that's using random numbers is actually using readran from Intel, you can override this, or if you have control over that, and you can change timing information to figure out what the internal state of the random number generator is. There's a lot of different places that randomness is used. So there's more general places you can do. You can Trojan the OS image. You can look for data from, if you need pieces of randomness to extract the rest, extrapolate, most protocols use random values. IVs, nonces, this kind of stuff. It's pretty interesting. And so like Heartbleed was something that came out recently. Like if you can extract the random number state through remote memory disclosure, something that you have, some 0-day memory disclosure, that can be even better than just extracting a specific key, because that can allow you to, as it goes forward, predict different things. So some examples from history, like in Debian, there was a problem with the RNG for generating RSA at one point. They missed like a line of code. For ECDSA, historical context, Sony PlayStation 2, they had this issue, and someone compromised the master signing key. More recently, the Android wallet for Bitcoin. This is kind of where I based my proof of concept on. They had often repeating values for the K used to sign things, and people stole at least 50 Bitcoins, maybe more, because of that. And more recently, iOS 7, the bootloader RNG they switched it from something secure to something less secure. And this is kind of allows you to do jailbreaking and these kind of things. More targets. This is just like thinking about where randomness is used on the internet is, well, session cookies. These are just also random tokens most of the time. So if you can predict that, you can steal people's accounts. You can log in as them. All these sort of web security things that rely on one-time generated secrets, those are all ownable. DNS poisoning attack, this is like from 10 years ago or so, relies on randomness of ports. And if you have visibility into the DNS server and the random state of that, then you could potentially do the DNS poisoning attacks that people thought were a thing of the past. This is something that's very, the next one is like the ECDSA certificate authorities. This is something that's a little more far out because we have auditing, right? So if you have a CA and it happens to sign an intermediate CA or a certificate twice with the same value, then it's done. You have to revoke the whole thing. And revocation, as I said earlier, is completely broken on the internet. And in conclusion, randomness is very important. It's the substrate that holds up cryptography in a lot of cases. And subverting this pseudo-random number generator can be done in different ways. And it's hard to detect. So it's a really great attack vector. And finding bugs is fun in random number generator. So repeated random in DSA, anywhere it's used, it's broken. So watch where you use DSA. And that's it. So thanks for listening.